The circulation of blood throughout our body is the result of the rhythmic contraction of the heart. The origination of each beat occurs within the heart itself. The contraction of the heart is the result of two types of cardiac muscle cells, autorhythmic fibers and contractile fibers. Autorhythmic fibers do not contract, but create and transmit the action potential, which stimulates the contractile fibers to shorten. Contractile fibers make up the bulk of the heart and are responsible for the movement of blood. There are bundles of autorhythmic fibers that establish the rate at which the heart contracts. The bundle that creates the action potential most rapidly is found in the right atrium and is known as the sinoatrial node, or SA node. The SA node not only stimulates the atrial muscle to contract, but also initiates an action potential in the ventricles. The atrioventricular node, or AV node, which is connected to the SA node by intranodal bundles, carries the action potential from the atria to the ventricles. The transmission of the action potential from the atria to the ventricles passes through the AV node at a slower rate, allowing the atria time to contract, maximizing the filling of the ventricles. After leaving the AV node, the autorhythmic fibers form the AV bundle, or bundle of His, which splits to carry the action potential to each ventricle via the bundle branches. From the bundle of His, each branch rapidly transmits the action potential through Purkinje fibers to stimulate ventricular muscle contraction. Although autorhythmic fibers each have the ability to create a rhythmic action potential, they do not do so at the same rate. Since all other autorhythmic fibers follow the lead of the fastest depolarizing area, the SA node is commonly referred to as the pacemaker of the heart. The SA node depolarizes during rest at about 70 to 80 beats per minute. If the SA node becomes non-functional or its transmission to the ventricles is interrupted, the AV node can become the ventricular pacemaker at 40 to 60 beats per minute. If the AV node is unable to pace the heart, the bundle of His and Purkinje fibers can pace the ventricular myocardium at 20 to 40 beats per minute. We will begin the description of the generation of the autorhythmic cell action potential as the membrane is repolarizing from the previous stimulating wave. Autorhythmic fibers do not have a resting potential because the membrane potential is continuously changing. As positive potassium ions diffuse out of the membrane, the inside of the membrane becomes more negative. We will chart the changes in electrical potential in millivolts that occur over time on the inside of the membrane. The generation of the next action potential begins when the electrical potential on the inside of the membrane reverses direction. This is caused by F-type sodium channels. They have the unique property of opening wider as the voltage inside the membrane becomes more negative, below -50 millivolts. As the F-type channels open, the increasing influx of positively charged sodium ions causes the membrane potential to become more positive. As the membrane potential heads in the positive direction, F-type channels close. A special type of calcium channel, known as a T-type channel, temporarily opens to allow positive calcium ions to diffuse in. This causes the membrane potential to reach a more positive value of -40 millivolts, the threshold which stimulates the generation of an action potential. Once the threshold of -40 millivolts has been reached, T-type calcium channels close. Then another type of calcium channel, known as the L-type channel, opens to allow the rapid inward diffusion of calcium ions. This causes the membrane of the autorhythmic cells to depolarize to 0 millivolts, as negative charges inside the membrane are canceled by the addition of positively charged calcium ions. At the same time, potassium channels are also stimulated, though they open slowly. As the potassium channels open and potassium ions diffuse out of the cell, the L-type calcium channels close, blocking the entrance of any more calcium ions into the cell. The loss of positively charged potassium ions on the inside of the cell membrane causes the membrane to become negatively charged again, or repolarized. The same sequence of events occurs beat by beat throughout our life. It is the depolarization and repolarization of the autorhythmic fibers that creates the action potential to stimulate contraction of the contractile fibers. The stimulus from the autorhythmic fibers spreads through gap junctions to the next cardiac muscle cell, transmitting the action potential throughout the heart. Connections between cardiac muscle cells, known as intercalated discs, bind muscle cells end to end. These connections contain both desmosomes to provide a strong bond between cells and gap junctions to conduct the action potential from one muscle cell to the next. The autorhythmic stimulus causes 4 voltage-gated channels in the contractile muscle cell membrane to open. It is the speed at which the channels open that determines the sequence of events involved in muscle contraction. The first voltage-gated channel to open is the fast sodium channel. Sodium ions rapidly diffuse, resulting in the depolarization of the contractile fiber membrane to stimulate muscle contraction. As the inside of the membrane depolarizes, fast sodium channels close and fast potassium channels open, allowing potassium ions to diffuse out, causing the membrane to begin to move in the negative direction. Very shortly after the fast potassium channels open, L-type calcium channels open. Calcium ions diffuse in to balance the outward movement of potassium ions and keep the membrane depolarized at 0 millivolts for an extended period of time. Elevated intracellular calcium causes the cardiac muscle to remain contracted long enough for blood to move out of each chamber. Finally, slow potassium channels open as the calcium channels close, resulting in the complete repolarization of the membrane to -90 millivolts and allowing the cardiac muscle to relax. Stimulated by the action potential from the autorhythmic fibers, the depolarization and repolarization of the contractile fibers membrane results in well-timed cardiac muscle contractions capable of moving blood through the cardiovascular system. Monitoring the electrical stimulation of cardiac muscle on the surface of the body is known as the electrocardiogram, or ECG. It is important to note that the ECG indicates the sum depolarization and repolarization of cardiac muscle and not its contraction. The ECG contains 3 basic waves. The P wave occurs as the atria depolarize. Once the stimulation reaches all of the atria, the wave returns to its baseline. The second wave is the Qrs complex, which indicates the depolarization of the ventricles. This is a larger wave than the P wave due to the greater mass of depolarizing muscle in the ventricles than in the atria. During the Qrs complex, the atria also repolarize, but the bulk of the ventricular muscle depolarizing creates a wave so large it overshadows the atrial repolarization. The final wave is the T wave, which indicates the repolarization of the ventricles, allowing the ventricles to relax. Physicians look for abnormalities in the shape or timing of the electrocardiogram as a means of diagnosing the condition of the heart. If we just consider the individual at a resting heart rate of 75 beats per minute, their heart beats 4,500 times in an hour, or 108,000 times every 24 hours. The process begins only a few weeks after conception and continues non-stop throughout our life. The constant circulation of blood throughout the body is critical to life. It is the pumping of the heart that provides the force needed to move blood through 60 to 100,000 miles of blood vessels, thus allowing for the exchange of gases, nutrients, and wastes for the trillions of cells in our bodies. The heart acts as 2 side-by-side pumps. The right side, responsible for pulmonary circulation, pumps oxygen-poor blood from the body to the lungs. The relatively lower pressure in the right side of the heart protects the delicate tissue of the lungs. and allows the thinnest possible barrier between the air in the lungs and the capillaries. At the same time, the left side pumps oxygen-rich blood at higher pressure to the body via systemic circulation. The heart has 4 distinct chambers. The upper 2 chambers, the atria, constantly receive blood. The lower 2 chambers, the ventricles, function as pumps to provide the force needed to push blood through the system of vessels circulating throughout the body. The direction of blood flow through the heart is maintained by 4 one-way valves. The atrioventricular valves prevent blood from flowing back into the atria during ventricular contraction. The semilunar valves prevent the flow of blood back from the pulmonary trunk and aorta into the relaxed ventricles. When heart valves close, vibrations occur within the ventricles and blood vessels that can be heard through a stethoscope. The cardiac cycle has 5 phases and includes all of the events that occur during a single normal heartbeat. Phase 1 is passive ventricular filling. All of the chambers are relaxed, as most of the blood from each atrium passively flows through the open atrioventricular valve into its respective ventricle. Atrial contraction is the second phase of the cycle. The atria contract, forcing additional blood into the ventricles. Atrial contraction causes ventricular blood volume to reach its maximum. Phase 3, isovolumic ventricular contraction, occurs as the ventricles begin to contract. Pressure rapidly increases within each ventricle, forcing the atrioventricular valves to close. Since both atrioventricular valves and both semilunar valves are closed, blood pressure within the ventricles increases, but the blood volume actually remains unchanged. This is said to be isovolumetric. Ventricular ejection is the 4th phase of the cardiac cycle. As ventricular contraction continues, the pressure inside the ventricles eventually exceeds the back pressure in the pulmonary trunk and aorta. This forces the semilunar valves to open, and blood from the ventricles is pushed into these great vessels. In a resting adult, slightly more than half of the blood, approximately 70 milliliters, is ejected each time the ventricles contract. The combined 3rd and 4th phases of the cardiac cycle, when the ventricles are contracting, are known as systole. The final phase, isovolumetric ventricular relaxation, occurs when the ventricles begin to relax. When the pressure in the ventricles becomes less than in the great vessels, the back pressure pushes the semilunar valves closed. Because all 4 valves are again closed as the ventricles relax, there is no change in blood volume, causing a second iso state, known as isovolumetric ventricular relaxation. From this phase until the start of the next ventricular contraction is known as diastole. Each cardiac cycle lasts about 0.8 seconds, a resting adult heart rate of approximately 75 cycles per minute. Even though there is continual contraction throughout life, this muscle never tires because the ventricles are in systole for only 0.3 seconds and diastole for approximately 0.5 seconds. The ability to rest for more than half of the cardiac cycle is sufficient to maintain normal heart function. During strenuous activity, like exercise, the heart has the ability to increase its output by 4 to 5 times. It is an organ of amazing design and capacity.
In order for the heart to function properly, its cells must contract in a specific sequence. A pathway known as the conduction system determines this sequence. The heart's unique conduction system works because of cardiac muscle cells that are both connective and autorhythmic. Autorhythmic cells spontaneously generate and spread action potentials from fiber to fiber across gap junctions. This triggers the networked heart fibers to contract in a regular rhythm. Cells from different parts of the heart have different natural rhythms, ranging from 100 action potentials, or beats per minute, in the sinoatrial node, to 40 to 50 beats in the atrioventricular node, to only 20 to 40 beats in the ventricles. The SA node is known as the healthy heart's pacemaker. Action potentials generated from the SA node spread to other areas of the conduction system and trigger contraction before the other areas are able to generate action potentials at their own slower rate. As the action potentials move through the atria and reach the AV node, the atria contract, moving blood into the ventricles. Typically, the AV node is the only connection between the atria and the ventricles. As the wave of excitation passes the AV node, it proceeds to the AV bundle and bundle branches, the apex of the ventricular myocardium. The conduction myofibers then directly stimulate the cardiac cells in the ventricles to contract. During ventricular contraction, blood is squeezed out from the apex to the base and into the pulmonary trunk and aorta. The signal moves quickly from the SA node through the atria. It experiences a slight delay when it reaches the AV node, as it must pass into fibers with smaller diameters. The signal then quickly resumes along its path, through the AV bundle and branches, apex, and base of the ventricles. Contraction begins. The sequence of depolarizations and repolarizations can be seen in a normal electrocardiogram, usually called an ECG. The electrocardiogram can also show problems with the conduction system. Look at this trace showing complete heart block. By comparing the QRS waves to the P waves, you can see that ventricular excitation is independent of atrial excitation. The pace of ventricular contraction is being set by the ventricle's slower natural rhythm, not by stimulation from the SA node and atria. A typical contractile cell in the myocardium has a resting membrane potential. Cells in the SA node do not have a fixed resting membrane potential. Instead, the resting membrane potential of an SA node cell is called a pacemaker potential. Each healthy heartbeat starts with a pacemaker potential, in which the autorhythmic cells of the quick-firing SA node spontaneously excite themselves and neighboring cells. The cell's membrane potential gradually becomes more positive until threshold is reached. This triggers rapid depolarization, sending the contraction signal on its way. Repolarization follows, and the SA nodal cell is ready to fire again. In ventricular cells, an action potential has 4 stages. The resting membrane potential is steady until a stimulus causes it to exceed threshold, triggering rapid depolarization, which is followed by the plateau, during which the cell remains depolarized. The plateau is followed by repolarization, after which the cell returns to the resting potential. The SA node's rate of firing, combined with modifications from the autonomic nervous system, determines the heart rate. The autonomic nervous system can modify the heart's rate in 2 ways. The hormone acetylcholine, secreted from parasympathetic neurons, decreases SA node firing to about 75 action potentials per minute, decreasing heart rate. This heart rate is considered normal and healthy for a resting heart. Conversely, norepinephrine increases heart rate. This hormone, secreted from sympathetic neurons, is produced more during exercise, stress, and excitement. The heart beats about 100,000 times each day. One heartbeat consists of a cycle of events that lasts about 0.8 of a second. Each cycle includes the contraction and relaxation of both the atria and the ventricles. In each chamber of the heart, the sequence of activity begins with excitation. Excitation causes contraction. Contraction increases blood pressure. Changes in pressure cause the opening and closing of heart valves, regulating the volume and flow of blood. Timing of the sequence depends on the amount of electrical activity in the heart muscle. Electrical changes during the cardiac cycle can be seen on an electrocardiogram, or ECG. Electrodes placed on the skin detect changes in the heart's electrical activity. The P wave indicates atrial excitation. The QRS wave indicates ventricular excitation. The T wave indicates the end of ventricular excitation. The heart beats about 100,000 times each day. One heartbeat consists of a cycle of events that lasts about 0.8 of a second. Each cycle includes the contraction and relaxation of both the atria and the ventricles. In each chamber of the heart, the sequence of activity begins with excitation. Excitation causes contraction. Contraction increases blood pressure. Changes in pressure cause the opening and closing of heart valves, regulating the volume and flow of blood. Timing of the sequence depends on the amount of electrical activity in the heart muscle. Electrical changes during the cardiac cycle can be seen on an electrocardiogram, or ECG. Electrodes placed on the skin detect changes in the heart's electrical activity. The P wave indicates atrial excitation. The QRS wave indicates ventricular excitation. The T wave indicates the end of ventricular excitation. Atrial contraction, or systole, initiates the cardiac cycle. Phases that follow are isovolumetric contraction, ventricular ejection, isovolumetric relaxation, and ventricular filling. Prior to atrial contraction, the atria and ventricles are relaxed. Atrioventricular valves are open, and semilunar valves are closed. The ventricles fill with blood. Depolarization triggers atrial contraction. Contraction increases atrial pressure and pushes extra blood into the ventricles, slightly increasing ventricular pressure. The excitation triggers ventricular contraction. Ventricular contraction is at first isovolumetric. This means that ventricular blood volume and muscle cell length do not change. Contraction causes ventricular pressure to rise above atrial pressure, forcing the AV valves shut. With the valves closed, the continuing contraction increases ventricular pressure. Ventricular ejection takes place when ventricular pressure rises above arterial pressure and the semilunar valves open. The valves stay open for about a quarter second. As blood is ejected into the arteries, ventricular volume decreases. Ventricles begin to repolarize and relax, ventricular pressure decreases, and contraction ends. Repolarization of the ventricular muscle cells initiates isovolumetric relaxation. As the ventricles relax, pressure in the ventricles drops. Semilunar valves close, preventing backflow. The closure produces a dicrotic wave on the aortic pressure curve. With both semilunar and AV valves closed, blood volume does not change. This isovolumetric relaxation sees pressure drop quickly. Ventricular filling occurs as all four chambers of the heart are relaxed and the AV valves open. As the valves open, the ventricles begin filling with blood. In about 0.2 of a second, blood that has been building up in the atria rushes in to fill the ventricles. Atrial depolarization triggers atrial contraction, forcing a small amount of extra blood into the ventricles, and a new cardiac cycle begins. There are two major heart sounds that make up a heartbeat. They are known as S1 and S2. The heart sounds result from audible blood turbulences of blood flow caused by the closing of heart valves. The S1 sound is described as a lub sound. It's louder and lasts a bit longer than the S2 sound. S1 is produced by the closure of AV valves and marks the start of ventricular contraction. The S2 sound is described as a dup. Its pitch is higher and sharper than S1. S2 is produced by the closure of SL valves and marks the start of ventricular relaxation. The sounds together form the heartbeat and sound like lub dup. The pumping action of the heart maintains blood flow throughout the human body. Cardiac output is a measure of blood flow. It is the volume of blood ejected from the heart over a given time. Cardiac output is determined by multiplying heart rate by stroke volume. Cardiac output in the typical resting heart is about 5 liters per minute. Cardiac output is not constant. It varies with the body's metabolic demands. Mild exercise will double cardiac output, while an intense workout can increase output as much as 4-fold to 20 liters of blood each minute. Stroke volume is directly correlated with cardiac output. The greater the stroke volume, the greater the cardiac output. Stroke volume represents the difference in the amount of blood between the volume in the ventricles at the end of diastole and the volume after systole. Three factors increase stroke volume: increased preload, increased contractility, and decreased afterload. Preload is the degree of stretch of cardiac muscle cells prior to contraction. The amount of stretch is related to the end diastolic volume. Increased return blood flow from the veins increases end diastolic volume. Cardiac muscle sarcomeres stretch and lengthen. Contraction of the cardiac muscle sarcomeres during ventricular systole provides the force to eject blood from the heart. Sarcomere length affects muscle tension and the force of contraction. An increase in muscle stretch increases tension. A more forceful contraction ejects more blood, thus increasing stroke volume. The relationship between preload stretch and stroke volume is known as the Frank-Starling law of the heart. The greater the preload, the greater the sarcomere stretch, the greater the stroke volume. The Frank-Starling law has limits. When cardiac muscle is overstretched, increasing ventricular filling has no significant effect on stroke volume. Contractility is the forcefulness of cardiac muscle contraction. Inotropic agents can increase or decrease contractility at any given level of stretch. Positive inotropic agents increase contractility, thereby increasing stroke volume and cardiac output. Negative inotropic agents reduce force of contraction. Positive inotropic agents include neurotransmitters, hormones, and some drugs. Certain drugs, such as calcium channel blockers and some anesthetics, are negative inotropic agents and reduce contractility. Afterload is the pressure or force that the ventricles must overcome to push open the semilunar valves and eject blood. Blood pressure in the left ventricle must overcome arterial pressure in the aorta in order to open the aortic valve. Hypertension increases aortic pressure, and the left ventricle must work harder to generate the pressure required to maintain stroke volume and cardiac output. Eventually, ventricular pressure builds to overcome the elevated arterial blood pressure, and blood is ejected from the heart. As afterload increases, ejection is more difficult, and both stroke volume and cardiac output are diminished. The ventricles compensate for decreased cardiac output in two ways: by activating feedback mechanisms that increase preload, and by initiating hypertrophy in cardiac muscle cells to increase contractility. The sinoatrial node normally initiates 60 to 100 heartbeats per minute. A normal resting heart rate is about 75 beats per minute. Heart rate and cardiac output are directly proportional to one another. The greater the heart rate, the greater the cardiac output. Heart rate is influenced by such conditions as exercise, stress, blood loss, and tissue damage. More importantly, the autonomic nervous system and hormones play key roles in the regulation of heart rate. A decrease in blood pressure promotes sympathetic stimulation, the release of norepinephrine, and thus an increase in heart rate and cardiac output. An increase in blood pressure promotes parasympathetic stimulation, the release of acetylcholine, resulting in a decrease in heart rate and cardiac output. The hormones epinephrine and norepinephrine, secreted from the adrenal gland, as well as thyroxine, accelerate heart rate. Low blood oxygen and pH, as well as high blood carbon dioxide, also trigger an increased heart rate. Additionally, moderate increases in cytosolic levels of ionic calcium also increase heart rate. The autonomic nervous system can modify the heart's rate in two ways. The hormone acetylcholine, secreted from parasympathetic neurons, decreases SA node firing to about 75 action potentials per minute, decreasing heart rate. This heart rate is considered normal and healthy for a resting heart. Conversely, norepinephrine increases heart rate. This hormone, secreted from sympathetic neurons, is produced more during exercise, stress, and excitement. Cardiac output is not constant. It varies with the body's metabolic demands. Mild exercise will double cardiac output, while an intense workout can increase output as much as fourfold to 20 liters of blood each minute.